Imagine you're teaching a robot to catch a ball. You could show it thousands of videos of balls being thrown. Eventually the robot would get pretty good at predicting where the ball will land, just by recognizing patterns. This is how standard artificial intelligence, or AI, learns. It's a powerful method, but it's like learning through pure memorization. The robot doesn't actually understand why the ball moves the way it does. It doesn't know about gravity, air resistance, or momentum. It just knows that in the videos it saw, the ball usually followed a certain arc. It's a student who aces the test by cramming, not by understanding the subject. Now let's introduce a new kind of student, a physics-informed neural network, or PIN. A PIN is a special type of AI that doesn't just learn from data, it also learns from the laws of physics. Think of it as giving our robot a physics textbook along with the videos. While it watches the ball's flight, it also cross-references what it sees with the rules of gravity. It learns that objects accelerate downwards at 9.8 meters per second squared. This fundamental knowledge makes its predictions smarter, more accurate, and more reliable, especially when it sees a situation it has never encountered before. This combination of data and physical laws is what makes PINs so revolutionary. They bridge the gap between two powerful worlds: the pattern recognition abilities of deep learning and the time-tested fundamental principles of physics. Instead of just being a pattern matcher, the AI becomes a problem solver that understands the underlying mechanics of the world it's observing. It's not just memorizing the answers, it's learning the formulas. This allows it to make educated guesses and fill in the blanks where data is missing, because it can rely on the unbreakable rules of the universe to guide it. So in simple terms, a PIN is an AI that has been sent to physics school. It's a smarter, more insightful model that can understand the why behind what it sees, not just the what. This is a huge leap forward, especially in fields where understanding the underlying physics is critical. It transforms AI from a clever mimic into a genuine digital scientist, capable of reasoning about the physical world in a way that was previously out of reach. This is not just a small step, it's a giant leap for machine kind. So, how do we actually get an AI to read and obey a physics textbook? It's a fascinating process that happens during the AI's training. It's like a student being graded on two separate assignments. The first assignment is the traditional one. How well does the AI's prediction match the data it was given? For our ball-catching robot, this means comparing its predicted ball path to the actual path in the video. The closer the prediction, the better its score. This part is standard for almost all machine learning models. It's how they learn to spot patterns from examples. The second assignment is where the physics-informed magic happens. We give the AI a second score based on how well its predictions follow the laws of physics. These laws are written as mathematical equations, like the equations for motion or fluid dynamics. The AI makes a prediction and then we check if that prediction violates any of these fundamental rules. For instance, does the predicted path of the ball correctly account for the force of gravity? If the AI predicts the ball will suddenly fly upwards for no reason, it fails the physics test. This failure is turned into a penalty, a physics loss, that tells the AI to try again. The AI's ultimate goal is to get the best possible grade, which means minimizing the errors from both assignments at the same time. It has to find a solution that not only fits the data it sees, but also strictly adheres to the governing physical principles. It's a balancing act. The AI adjusts its internal connections, its neurons, over and over again, trying to reduce both the data error and the physics error. This process forces the AI to discover solutions that are physically plausible. It can't just connect the dots, it has to connect them in a way that makes sense in the real world. This dual objective training is what makes PINs so powerful. They don't need massive datasets to learn effectively. A traditional AI might need to see 1 million thrown balls to learn well. A PIN, however, can learn from just a few examples because the laws of physics provide strong guidance, filling in the gaps where data is scarce. The physics equations act as a powerful form of regularization, preventing the model from making wild, unrealistic predictions. It's like having a wise old professor constantly looking over your shoulder, making sure your work is not just correct, but also logical. Now let's bring this into the world of computer vision, where AI learns to interpret and understand images and videos. The impact of PINs here is profound, turning simple pixel analysis into a deep understanding of physical processes. Consider medical imaging, like an MRI scan of blood flowing through an artery. A standard AI could learn to identify a blockage by looking at many scans of healthy and unhealthy arteries. It's recognizing a visual pattern. A pin, on the other hand, can do much more. It can look at a sequence of MRI images and, guided by the laws of fluid dynamics, create a detailed dynamic model of the blood flow. This allows doctors to see things that the raw images don't show, like the precise pressure and velocity of blood around the blockage. The pin is essentially running a physics simulation directly on the patient's data, offering insights that could lead to better diagnoses and treatment plans. It's not just identifying a problem, it's explaining the physics of the problem. This is a game changer for personalized medicine, where understanding the unique dynamics within a patient's body is crucial for effective care. The AI becomes a diagnostic tool that can see beyond the visible data. Another exciting area is motion prediction for things like self-driving cars or robotics. A self-driving car needs to predict how other cars, pedestrians, and objects will move. A standard AI does this based on past observations, but what about a sudden, unexpected event like a ball rolling into the street? A pin, understanding the physics of motion, can make a much more robust prediction. It knows that the ball will follow a predictable path due to gravity and friction, and it can anticipate where it will end up, allowing the car to react more safely and intelligently. Pins are also transforming the creation of realistic simulations for movies, video games, and engineering. Creating realistic-looking smoke, fire, or water in computer graphics traditionally requires immense computational power to solve complex physics equations. Pins can learn these dynamics and generate stunningly realistic animations much more efficiently. They can take a short video of a real-world phenomenon like a waterfall and use it to learn the underlying physics of water flow. Then, they can generate new photorealistic waterfall animations under different conditions, all while obeying the laws of nature. The key advantage of pins over traditional deep learning models is their ability to work with sparse or incomplete data. Conventional AI is data-hungry. It needs vast, comprehensive data sets to learn effectively. If there are gaps in the data, it struggles to make accurate predictions. Pins, however, use the laws of physics as a universal source of information. Physics is always there, filling in the blanks. This makes them incredibly valuable in scientific and engineering fields where collecting data can be expensive, difficult, or even impossible. Think about modeling climate change or predicting cosmic events. We can't run those experiments in a lab. This leads to another major benefit: generalization. A model that understands underlying principles is far better at handling new, unseen scenarios. A standard AI trained only on videos of red balls might be confused by a blue ball. A pin, however, knows that the color of the ball doesn't change how gravity affects it. Its knowledge is more fundamental, allowing it to generalize its learning to a much wider range of situations. This makes pin-powered systems more robust and trustworthy, which is essential for critical applications in medicine, autonomous systems, and industrial design. Furthermore, the models produced by pins are often more interpretable. When a traditional AI makes a prediction, it can sometimes feel like a black box. We know the answer it gave, but we don't always know why. Because pins are constrained by physics, their results are grounded in established scientific laws. We can check their work against these laws, making it easier to understand and trust their outputs. This transparency is crucial for scientists and engineers who need to validate the results of a model before using them to make important decisions. In conclusion, physics-informed neural networks represent a wonderful fusion of human knowledge and machine intelligence. By embedding the fundamental rules of the universe directly into the learning process, we are creating AI that doesn't just see pixels but understands the world they represent. For researchers, engineers, and anyone excited about the future of technology, pins offer a pathway to building more intelligent, reliable, and insightful systems. They are helping us solve some of the toughest challenges in science and engineering, proving that sometimes the best way to leap forward is to build on the unshakable foundation of what we already know to be true. Consider it.